So, first of all, I'd like to thank the organizers for the very interesting workshop. And today is my talk is on the iron selenium-based superconductors. So we have to switch gear. And so here is the outline of my talk. First, I'd like to discuss the electronic phase diagrams of these iron selenium-based superconductors. And I prepared two topics. One is on this sulfur substituted iron selenium, and second is beryllium compound. So this work has been done in collaboration with many people, and I don't have time to call all the names, but I really acknowledge the beautiful collaboration with people listed here. Okay, so let me start with the introduction on this iron selenium. So I think all of you know this material, and this is a very intriguing material, and it has a very simple crystal structures, and notably it has nematic transition at 90 Kelvin with no magnetic order down to 0 temperature. And if you apply a hydrostatic pressure, then Tc goes up from 9 Kelvin to like 40 Kelvin. However, there is a kind of pressure-induced magnetic phase, so that hindered the relationship between the non-magnetic nematic phase and superconductivity. So we have been working on the isovalent substitution systems. So here is iron selenium, and the left-hand side, we substitute selenium. This is isovalent to the, this is the sulfur, which is isovalent to the selenium. And then we can also compare with the iron selenium, tellurium, another isovalent systems. And in both cases, you can suppress the nematic transition temperature, like here. And in this phase diagram, we have two kinds of nematic quantum critical point. One is here in the sulfur side, and one is here in tellurium side. And what is most interesting in this material is that this Tc shows a very characteristic, composition dependence like this. And we have actually two superconducting domes. And we actually separate these superconducting states into three phases. And here is SC1, which has a one dome here, and the SC2 with the suppressed Tc, which is outside the nematic phase in the sulfur side. And here is SC3, which have a highest Tc dome, okay? And there is a very beautiful NMR work by Furukawa-san in Ames, who found a strong correlation between this Tc and the NMR 1/T1T. So this indicates that, although there is no magnetic order in this, phase diagram, but there is some kind of remnant spin fluctuations, which is responsible for the superconductivity in this SC1. However, if you go to SC3 dome, if you measure 1/T1T, you don't see any enhancement. So this means that there is no significant spin fluctuations, at least in the low energy regime. So I think this superconducting dome is unrelated to the spin fluctuations. And then this SC3 is roughly centered around this nematic QCP. So we have a correlation between the nematic QCP and SC3 dome. And indeed, if you apply a strong magnetic field along the C-axis, you can suppress superconductivity, and now you have actually independent two superconducting domes like this. So this SC1 and SC2 can be quickly suppressed by magnetic field. However, SC3 is very robust against magnetic field, and even at 45 Tesla, we see the superconducting dome surrounded by this nematic QCP. So, and from the temperature dependence of the HC2, we can estimate the Pauli limiting field, which is a measure of the pairing strength, because H Pauli divided by TC is related to the superconducting gap to TC ratio, and it shows very large value compared to the BCS theory, and there is a tendency towards the enhancement to the QCP point. So this indicates that we have some kind of enhancement mechanism of the pairing strength near the QCP. So from this result, we conclude that nematic fluctuations, which are emanating from the QCP here, can enhance the pairing strength of the field robust superconductivity. So I think this is a very interesting superconducting system. And if we go back to this superconductivity phase diagram, we can also study the superconducting gap structure in these three phases. In SC1, this is the temperature dependence of the specific heat, C over T, which shows a T linear behavior at low temperatures. And also STM DRDB shows a B shape at low energies. So that indicates that superconducting gap shows a very strong anisotropy. And this is consistent with the analysis of the quasi-particle interference, which also shows a strong anisotropy. However, if you go to the SC3 phase, C over T is now showing the very flat behavior at low temperatures, and tunneling conductance shows a U shape like this. So it changes to a really fully gapped superconducting state. So the superconducting gap point of view, this SC1 and SC3 are also different. And this is consistent with the different origins of SC1 and SC3. And probably, SC1 is related to the spin fluctuation, and SC3 is likely related to the nematic fluctuations. Now, if you go to SC2, in the tetragonal phase of iron, selenium, sulfur, these superconducting gap shows a very anomalous behavior. So this is C over T, which shows a very large residual density of states. And also STM shows very damped features with finite zero bias conductance. And I would like to emphasize that this is not due to some sample inhomogeneity, because we can clearly see the quantum oscillation throughout this phase diagram, SC1 and SC2. So I think this is kind of intrinsic feature. And so now let me discuss on this SC2, very strange behavior of superconducting gap in the tetragonal iron, selenium, sulfur. And before that, I would like to just, remind you the general classification of the superconducting gap. And you have fully gap state or point node or line nodal states in which you have a different energy dependence of low energy quasi-particle excitations. And if you have line nodes and if you apply a magnetic field, you can create the supercurrent around vortices that causes the so-called Doppler shift of quasi-particles. And indeed, you can induce the low energy density of states, which are called Borovic effect. And very recently, the theory suggests that you may find a new type of superconducting states, I think the fourth class, and in which you have two-dimensional nodes, which are called Bogoliubov-Fermi surfaces. And if this happens, you can find zero energy finite density of states, like a metal, even in the superconducting state. But to have this very exotic superconducting state, there is a very important ingredient, which is the time reversal symmetry must be broken in the superconducting state. So you can kind of understand roughly by saying that if you have a time reversal symmetry breaking, even in the absence of magnetic field, you may find some kind of spontaneous Borovic effect that can create low energy states. Then the Peter Hirschfeld group have shown that they have some calculations based on the iron selenium based electronic structure. and find some parameter range in which they find this, indeed these kind of Bogoliubov Fermi surfaces. And they call this ultra-nodal pair states. And if you have this kind of Bogoliubov Fermi surfaces, you can easily expect the finite residual density of states in C over T, or the zero energy tunneling density of states, which are consistent with what we have observed in this SC2 region. Okay, and they assume, importantly, they assume the time reversal symmetry is broken. And to check this idea, we have measured the zero field μSR in collaboration with Tomo Uemura at Triumph. And we find in these three samples, including iron selenium and the tetragonal iron selenium sulfur, we have found that the relaxation rate of NMR asymmetry shows the enhancement below TC, which indicated that the inside the superconducting state, we have some kind of internal magnetic field appearing inside the sample, which is a good indication that time reversal symmetry is broken, right? So at least in the SC2, we have kind of requirement to have this Bogoliubov Fermi surface that is the time reversal symmetry breaking. Now here's a kind of set of summary of what we have seen. So the upper panel is the phase diagram again. So this is the nematic transition as a function of sulfur composition. And TC shows a jump from SC1 to SC2, and SC2 has a lower TC. And then the STM zero bias conductance and the specific heat residual density of states both shows the abrupt jump. And we have this residual density of states only in SC2. And we also measure the transverse μSR, from which we determine the superfluid density, which is 1 over penetration depth squared, which we plot in the red points. And this 1 over lambda squared is proportional to the superconducting carrier density, and which can be compared with the normal state Fermi surface properties, which can be estimated from the quantum oscillation results, which is shown by this blue line. And as you can see in the tetragonal side, we have strong deviations. So meaning that, significant fraction of carriers remains ungapped in the superconducting state. And a very recent calculation by Sethi et al., this is Peter Hirschfeld group, they found that the superfluid density should be kind of suppressed in a parameter range in which you can find a stable Bogoliubov Fermi surface. So I think this is kind of consistent with what we have observed in μSR data. So from the combination of these results, we made a conclusion that we have evidence for ultra-nodal pair state with Bogoliubov Fermi surfaces in this SC2 phase of this material. Now, the Professor Okazaki group at ISSP have measured the laser RPS in this SC2 phase, and they found that the gap as a function of Fermi surface angle shows a very strong anisotropy. And they found extended angle range in which the superconducting gap does not open, actually. So this is consistent with the presence of the Bogoliubov Fermi surface. However, very interestingly, they found a strong twofold anisotropy, although the system is still in the tetragonal C4 phase. So there is some mechanism that can break the rotational symmetry only in the superconducting state. So we call this the nematic Bogoliubov Fermi surfaces. And the reason why we can have this kind of twofold symmetry is still under discussion. And I just want to show you that there are already two theoretical proposals for the origin of the nematic Bogoliubov Fermi surfaces, but we need further investigations. Now, another indication from NMR shows another interesting feature. And here is 1 over T1T as a function of temperature in the superconducting state of these three samples. And in this purple data is in the SC2 phase outside the nematic phase. And they found a very exotic increase of 1 over T1T at low temperatures. In the superconducting state, usually the 1 over T1T is going down as it's lower in temperature, but this enhancement may be related to the kind of spin fluctuations which you expect if you have this kind of Bogoliubov firm surface and you have a nesting behavior. So this is another interesting observation. Okay, so far so good. But very recently, the theoretical analysis by Andrei Chubkov shows another possibility. Okay, so they assume that if you have very close to the nematic QCP and calculate the gap anisotropy, and they found you may find a highly anisotropic superconducting gap like this. And so there is a kind of large region in which the gap is very small. But in this case, if you go to the zero temperature, this part becomes to the point. And so you should expect a downturn behavior of the specific heat. And so to check this idea, we actually measure the specific heat down to low temperature and also penetration depths down to 0.02 TC. But so far we haven't seen any downturn deviation. So we still see some very large residual density of states. And furthermore, they expect that if you go out far away from the nematic QCP, this curvature is going to dumped. However, we actually go to 0.25, which is kind of far away from the QCP, but we don't see this kind of behavior yet. And so we decided to fit our penetration depth data to this Bogoliubov firm surface picture. And here is a kind of model to describe the energy dependence of the quasi-particle density of states that can fit our penetration depth data very well. And we also study the disorder effect by using electron irradiation. Then we can actually suppress TC by adding the point effects and see how the penetration depth changes. And we can fit the low temperature data to a power law. And here is the exponent, the power exponent, n as a function of disorder. And we found that the exponent actually shoots up above the 2. This is an indication that we have changed the superconducting gap structure from nodal to nodeless, right? So this, to explain this result, we have a kind of idea that, original Bogoliubov firm surface is coming from the time reversal symmetry breaking effect, which is induced from the original accidental nodes, which is present on the original firm surface, right? And if in the iron-based superconductors, this nodes are known to accidental, which is not protected by symmetry. So if you put disorder, these nodes can be lifted by disorder, and at the same time, this Bogoliubov firm surface will be lifted. And after that, you can actually consider the Andreev band state, which is created by the sign-changing S plus minus wave-like state. Then the exponent becomes 2. Okay, so our conclusion is that the disorder induced by electron irradiation can lift the gap nodes, evidencing the accidental nature of Bogoliubov film surface, which are originally from the S-wave nodes. Okay. So in the last 3 minutes, let me discuss briefly about the iron selenium tellurium superconducting state. So another important feature of this phase diagram is that if you go to this SC3 phase, the electronic structure actually changes, and this P band, which is coming from the Chalcogenian site, is going down and making a cross near the Fermi level along the gamma Z line. So the electron structure in this SC3 phase is considered as topologically non-trivial, okay? And then there is RPS measurements showing that indeed on the surface, we have this kind of Dirac cone-like electronic structure, which is a topological surface state. And then you have superconductivity of TC is about 14 Kelvin. So there is a kind of, view, very interesting view that you can actually have a trivial superconducting state in the bulk, and on the surface, you have a topological surface superconducting state due to this topologically, topological electronic structure. And indeed, in these materials, if you measure the STM near the vortex cores, you can find the zero bias conductance peak, so which is an indication that we have a Majorana zero mode in this material. So these results are strongly suggesting that we have a topological superconductivity in this SC3 phase, and it is indeed a very intriguing system. However, very recently, the group of Peter Johnson have measured the RPS on this material and found that this Dirac cone is actually gapped below TC on the surface. So this suggests that you may have some kind of a time reversal symmetry breaking effect, at least on the surface of this topological superconducting state. So to check whether we have the time reversal symmetry breaking in the bulk, we have measured the zero field μSR in this series. Okay, so here is a result of tellurium of 0.35 and 0.6, and in both cases we see the enhancement of relaxation rate below TC, indicating that we have actually time reversal symmetry breaking throughout this phase diagram. And so at least from the μSR, we can say that this time reversal symmetry breaking is in bulk. So our kind of picture is that, previous picture, it can be, changed to a very interesting case that in the bulk, we have a time reversal symmetry breaking superconducting state. So this is not a trivial state already. And in the surface, we have a Dirac gap. So we have a kind of combination between the bulk unconventional superconductivity and topologically non-trivial electron structure. So I think this is quite a unique platform for studying topological superconductivity. Okay, so let me finish my talk by putting this summary slide. And first, I would like to discuss the electronic phase diagram and this SC3 region, this field robust superconducting dome is likely related to the nematic fluctuations. And in this, SC2 phase, we have evidence for the ultranodal superconducting state with Bogoliubov-Fermi surfaces, but these Bogoliubov-Fermi surfaces can be lifted by this order. And finally, I discussed the topological surface states accompanies bulk time reversal symmetry breaking in this iron tellurium, which may provide a very unique platform for the topological superconductivity. Okay, so that's it. Thank you very much for your attention.
Thank you, Taka, for a really nice talk. I really enjoyed it. Do we have any questions? Somebody sure to have one. Peter, especially.
Yeah, hello. Can you hear me?
Yes, we can, Peter.
Okay, good. So I was interested in the observations you made on obviously on the iron selenium tellurium system.
Right.
And here you have the slide. You have this relaxation rate, which I was pleased to see gets bigger as you get more tellurium into the system. That's at least that's how I'm reading E and F. Correct?
Right. Yes. Actually,
and so
points, these red points is the estimated internal field as a function of content. And in this 0.6, we have a much larger signal than the around here. So I think we have a nematic quantum critical point around 0.5. So there is some kind of a change in the superconducting state. And so
I don't know much about your well, I know something about your technique, but so my question is,
yes,
you have you have a relaxation rate above TC.
right. Yeah.
What do you associate that with? And then the linearity of the relaxation rate as you go below TC, what do you associate that with? I'm looking up in particular at this figure F.
This one.
Yeah.
Okay. Yeah. So in the normal state, you may have some kind of signal from nuclear and other maybe impurity or something. That's kind of usual. But the temperature dependence is telling important things, and you shoot up the relaxation rate. And I can add one more thing, that we can actually measure the longitudinal field μSR, which is plotted by this green, and you can recover this thing. So this indicates that this relaxation is coming from the static internal magnetic field rather than the fluctuating magnetic field. So this indicates that we have some kind of static field appearing inside the sample, which is coming from the superconductivity.
Yeah, but it's linear in temperature, and I'm asking what you associate that linearity with.
Okay. So the temperature dependence of this, so it's not really clear why we have this linear temperature dependence, but this means that the internal magnetic field is increasing, if you go to low temperature. And so, this internal magnetic field is expected if you have time reversal symmetry domains or impurity sites. So I think the temperature dependence is kind of very not easy to understand.
Okay.
But at least the result is consistent with your result.
Okay. Ping-Ching, you had a question?
Yeah. So I'm very curious, Taka. Very nice talk. I'm totally puzzled by this observation of a time reversal symmetry breaking 0.6. Are you actually suggesting the superconductivity is actually induced by sort of static ferromagnetic order, like a spin triplet? I mean, is that what you're suggesting?
No. In this material, there is there are many interactions, pairing interactions, and in terms of symmetry. So you can actually have S wave or D wave symmetry which cross. In such a case, you can have time reversal symmetric breaking, such as S plus ID or something like that. So this is nothing to do with the ferromagnetism. So the superconducting other parameter can break the time reversal symmetry.
I see. But I mean, okay. But so there's really no ferromagnetic impurity. I mean, it's known that you have a potentially excess iron and things like that. I mean, there's no such thing in this regime of the phase diagram.
Right. So we were kind of carefully prepared the samples, and actually, if you go to this side, 0.8, we start to see the effect of the kind of
excess iron, right?
Short range thing, but which can be checked. The difference between this zero field and the longitudinal field is.
So, what is the volume fraction where you see this? You see this internal field?
Internal field is very small, but I can say that superconducting volume fraction is 100% from.
No. I'm asking this internal field. What is this volume fraction?
Okay, so it's not the magnetic order, so you cannot say that how many volume fraction. It's not a magnetic order. It's like you have a sparse field.
Okay,
inside.
okay.
Yeah.
Okay, thank you.
Meow.
So, let me just ask one more thing. So you're saying there's this internal field.
Right.
Which direction is that
Okay.
going?
So, we can change the, muon direction, and SR and NSR mode, it has a different geometry. And we find a larger signal from SR, meaning that it's likely related to the C-axis.
It is parallel to the C-axis.
That's right.
Jimmy-L, you had a question?
I did, but I think it was already answered. It was interesting knowing whether the superconductivity is about, and I think Taka, you said
Yes.
at the doping where
This
the
is
signal is the
100%.
largest, the superconductivity is about 100%.
Yes, the specific heat shows a 0.
Okay, thank you.
Great. So thank you, Taka, for a very nice talk, and I will turn it back to